Imagine yourself suspended between worlds, gazing out a small, curved window. Below you, a vast, brilliant white sea of clouds stretches to the horizon. The sky above is a deep, dark, and tranquil blue. The gentle hum of the engines is the only sound that breaks the stillness. You are cruising at 35,000 feet. A passenger in a metal tube hurtling through the stratosphere at over 500 miles per hour. It feels peaceful, almost serene. This specific altitude is not chosen by chance. It is a carefully calculated decision. Have you ever looked at the flight tracker? Wondered about that number? 35,000 feet. Why so high? Why not lower? Why not even higher? The answer is a dance of physics, engineering, economics, and safety. Each plays a critical role. It is about finding the perfect compromise. This journey to the upper troposphere is fundamental to modern air travel, a quiet promise of smooth, swift passage. Decades of learning woven into wings and engines. Let us peel back the layers: the air, the engines, the weather, and the rules that keep us safe. The most important reason begins with something we cannot see: the air itself. Down here on the ground, the air is thick and heavy. It is dense with molecules of nitrogen, oxygen, and other gases. Like walking through a pool, every step pushes against resistance, a force. Near the ground, an airplane battles this wall of molecules, drag. As it climbs, the atmosphere thins, molecules spread farther apart. At 35,000 feet, air density is under a quarter of sea level. Like swapping water for a lighter oil, movement faces less resistance. In thin air, far fewer molecules strike the aircraft. Drag drops dramatically. Less drag means less thrust required, so engines work less and burn less fuel. For airlines, fuel savings are survival, enabling affordable travel. At altitude, speed is maintained with less effort, like riding a tailwind. But go too high and lift dwindles. So we seek the thin air sweet spot. Low drag, yet enough lift. Now, the magnificent engines at the heart of a modern airliner. Not the propellers of old, but turbofan jet engines. Their operation is tied to altitude. A jet engine is air-breathing. It draws vast quantities of air, compresses it, mixes with fuel, ignites the mixture, and expels hot gas for thrust. At 35,000 feet, outside air hovers near -54 Celsius. Colder air, denser at the same pressure, helps compressors work efficiently. A greater temperature difference between intake and exhaust boosts cycle efficiency. Yes, ambient air is thin aloft, but the engine leverages the cold to its advantage. Modern turbofans are tuned for cruise, a marathon, not a sprint. They still deliver immense power for takeoff, but spend hours running steady, sustainable, highly efficient. At 35,000 feet, the engine sips fuel, runs cooler, and with less stress, extending lifespan and range. Beyond the physics, there is comfort and safety. Most weather we feel, rain, wind, thunderstorms, lives below, all of it in the troposphere, where clouds form and storms churn. Flying through, that can be bumpy, even dangerous. Climb to 35,000 feet, and you rise above most of it. Near the tropopause boundary, air is calmer and more stable. That is why flight can be perfectly smooth while storms rage below. It is not a perfect shield. Some storms breach cruise levels, and clear air bumps exist. Pilots use radar and forecasts, adjusting routes and levels to avoid trouble. But altitude is the first and best defense, a thick blanket of stable air between you and the turmoil. Smoother air also eases stress on the aircraft, reducing wear and maintenance burden. A gentler journey for people and machine alike. The sky seems empty, but it is structured and regulated. Like highways and signals on the ground, we use organized corridors in the air. It all relies on separation, horizontally and vertically. Altitude creates invisible highways stacked one atop another, standardized flight levels. Eastbound flights use odd altitudes like 33 or 35,000 feet. Westbound, even levels like 34 or 36. That enforces a 1,000-foot vertical buffer, dramatically reducing collision risk. Structure turns open sky into a predictable environment. Pilots request cruising altitude based on route, performance, and weather. ATC approves or assigns different levels to maintain safe separation. This constant communication is the invisible backbone of aviation safety. Stacking aircraft lets more planes use the same routes at once. 35,000 feet fits neatly as a standard long-haul level within this global system. An airliner does not just climb to 35,000 feet and stay there. As fuel burns and weight falls, the optimal altitude rises. Heavier early on, the plane cruises lower, 31 to 33,000 feet. Hours later, lighter, pilots coordinate a step climb, up to 35,000 feet, perhaps later to 37,000, tracking the efficiency sweet spot. Go lower and dense air drives drag and fuel burn up. The ride gets rougher. Go much higher and air gets too thin. Wings need dangerous speeds. Engines starve for oxygen. Margins shrink toward the coffin corner, not a place for airliners. So the cruise window is roughly 30 to 42,000 feet, with FL350 a frequent optimal choice. Air density, engine design, weather, aircraft weight, and traffic safety, all in harmony. The next time you fly, appreciate that carefully chosen slice of sky. Your smooth, quiet ride is a century's wisdom, balancing machine and nature.